Welcome to CircuitValley. I'm Gaurav. Today I'm going to show you one more project of mine. This project is going to be a distribution board, something like this. If you remember, very first few videos which I published on this channel was about this GPSDO. This small little unit, it has a GPSDO and a distribution board built in. So you see these four outputs. These distribution boards output, they are 10 megahertz isolated output. They are galvanically isolated from one another using transformer. So if you connect one instrument to here, it will not affect the another instrument or not will be ground connected to them. So they are both galvanically isolated. That's why you see this plastic VNC connector. GPSDO board, it has a distribution board built in. This is what I got a separate project now. So this is the device. This unit has 6 outputs, 1 input and 6 output. 4 outputs are in the front. You can see in the front, it's called DISTISO6. 6 means 6 output. Outputs are all 50 ohms, isolated distribution amplifier. On the back, you got the rest of the 2 outputs. To keep the unit size compact, I kept as 4 outputs in the front. And this distance between BNC to BNC is sufficient so that you can plug even the most thickest BNC cable, whatever you got. So this is very important. If I could have fit 5, maybe even 6 of them, but they will be very tightly packed, so you will not be able to plug anything reasonable there. Sometimes you have very thick BNC cables which have some plastic shrouds or some electronics built in, so you want to keep distance between the connectors. Distance between each connector is around how much? It is around 33-34 millimeters, so it's very sufficient to plug even the thickest BNC cable in there. And next thing you have is the output. Next thing you have is the power input. This is conveniently USB-C input. As there are more and more electronics with USB-C, and nowadays almost everybody has power supply with USB-C in there. So this port, it's supposed USB power delivery, so it automatically negotiates the power delivery, 12 volt or 15 volts. It will try to negotiate first 15 volts, and if it doesn't find 15 volt, then it will negotiate down to 12 volt. 12 and 15 are very common. Generally in laptop chargers which supports USB-C PD, you will find 15 volts. For example, Dell and HP and Lenovo all three have 15 volt supply. And for the cell phones, primarily small power supply, they will have 12 volts. So it will automatically try to negotiate 15 first. If it doesn't find 15, then it will negotiate down to 12. So if the power supply does not support 15, then it will be definitely supporting 12. And if it does not support 12, then it will be definitely supporting. It needs minimum 12 volts to function because there is an analog regulator in there. I'll show you a PCB board in a second. And other secondary power input is normal DC barrel jack. I think it's a 2mm center positive line. You can supply 12 to 24 volts. Consumes around 300 milliampere maximum with all 6 output terminated to 50 ohm. This is a power LED, so if you plug in the power, this power LED will lit up. And this is the input connector. This is 17 dBm max. Above that, there's a protection circuitry there, so it will not directly cause damage, but I would suggest to limit the input amplitude to 17 dBm max for the 190 megahertz, and under 100 megahertz is even lesser. So input is 50 ohms, output is all 50 ohms. They are all galvanically isolated. It is very nicely constructed unit. You can see very nice aluminum enclosure with very nice inputs and outputs, and everything is appropriately labeled using the overlay. It's very high quality overlay, and overall enclosure and finish is very solid. It's not going anywhere. Plastics are injection molded parts, and they are very well done. So this is how the PCB looks. It's a new revision of my old project, which is already open source. It's published many years ago on my website and also on the YouTube channel. So it's the same thing. Circuitry is based on AD8009, very powerful operational amplifier, and it drives into these transformers. One driver drives into 2 transformers and achieves the output amplitude of 30 dBm at 10 megahertz and around 11 dBm at 100 megahertz. This design has been working for many years, and this is the linear regulator for the power supply, and the both of the power supply inputs, USB-C input for the convenience, and if you have old style chargers, then you have this Parana barrel jack. This is the input, this is signal input, preamp, and all the distribution channel outputs. So now we will go to my spectrum analyzer. We will see how it looks and how it works on the spectrum analyzer, how clean the spectrum is, what is the output levels and everything else, how does this thing performs. To test the performance of this little distribution amplifier of mine, I'll first use this spectrum analyzer. I have set the span from 100 kilohertz to 250 megahertz so that I can show you the performance, how well it performs. We will first use the tracking generator of the instrument itself to show you that how linearly it performs over the spectrum of whole 190 megahertz. Let's see. plug it in. To power it, first I'll use USB-C power supply. You can of course use the barrel jack as well if you have power supply for it. So this is how it lights up. There is a bicolor LED and both red and blue color LED lights up. So now it expects input, and we will connect the tracking generator input to it. Something like this, very easily. And now I'll connect the tracking generator output as well. So as we got our input and output connected, and we will set the amplitude to reference level 10 dBm, and tracking generator level, it goes maximum to 0 dBm. I would love to try it at maybe 10 dBm input, but it doesn't go up to that. So we'll try it at 0 dBm, and now I'll turn on the tracking generator. So this is how it responds, and you see spectrum is from 100 kilohertz to 100 kilohertz to 500 megahertz. Maybe I'll set it to 250 megahertz so you can see more easily what are we dealing with. So this is how it responds, and this works really reliably. And this is the spectrum for 250 megahertz. And let's go to 500 megahertz back, and I'll show you where it started to roll off. So around 200 megahertz we start to see a decent roll off, and maybe you can use it up to 250 megahertz, but after that it will be too less of an amplitude, and after that it rolls really down. After that it's completely useless. You can use it with decent confidence up to 200 megahertz and works reliably well. At 10 megahertz you can see it's very decent. Let's maybe look at the spectrum of our 10 megahertz. Stop frequency 20 megahertz. So absolute rock solid flat response for such a small spectrum, and how long it stays there without any changes. Let's try 30 megahertz. So for 30 megahertz spectrum, absolute flat response. For 0 dBm input, you got 4 dBm output. A little bit of amplification is implemented on the input stage, so it does the job really well, really nicely implemented. You can of course change the resistors to change the gain as well, but it works reliably well. Now I will try to input normal 500 megahertz or similar frequency, and you will see how it works there. Now I'll try to apply a normal 10 megahertz, 20 megahertz, and up to 190 megahertz. We will see how it responds there. As a source, we'll use my Marconi 2024 RF signal generator to input the appropriate signal, and we will see how it responds. So let's turn on the signal generator. Now signal generator is on, and first maybe I'll show you how does it looks at 10 megahertz. So I have set my Marconi. So I have set my Marconi to 10 megahertz, and let's see how does it look. So it's showing us the frequency correct almost, and amplitude is a little bit less, a little bit dropped, maybe due to the cable, or maybe my Marconi is not calibrated for a long time. So let's see if we go up in the amplitude, how does it look. So Marconi goes up to, so when you go a little bit up to amplitude, this is how it looks. It has harmonics around 30 dB down, around 40 dB down to the primary carrier frequency. And let's see if we feed in this same signal into our signal distribution box, how does it look. So this is how it looks. I induce a little bit more harmonics, but at the 9 dBm, harmonics are around 45 dB down. So this signal is absolutely clean. If you look at the oscilloscope, it will be absolutely clean sine wave. Let's go up in the amplitude so that we can see that it works really well. Maybe we'll try first with the lower frequencies. I will try to set the span to 10 megahertz. And now we'll go to 1 megahertz in the signal input. So you got 1 megahertz 9 dBm input output. Let's go up in the amplitude a little bit. So again 1 megahertz 12 dBm output, and let's see, maybe we can decrease the bandwidth a little bit, so that we can see a cleaner sine wave. So this is how it looks. It's very decent, very clean, very sharp 1 megahertz tone, and our distribution amplifier is doing good job distributing it to 6 isolated channels. So I leave it to auto, and now I'll go up the frequency to this is 5 megahertz. Let's look at the peak. 5 megahertz, around 12 dBm. Maybe I'll increase the reference level one more time so that you can see it better. Reference level is now 20 dBm. Peak is at around 12 dBm. And of course, if you increase the signal input amplitude to 10 dBm input amplitude, then you get a decent 4 dBm of gain, of course, and you got decent 5 megahertz signal. Maybe I'll try even lower frequencies. I'll try to 500 kilohertz, and I'll feed in, and you see this 200 kilohertz, very decent, 14 dBm, very high amplitude. And now I can jump to higher amplitude frequencies. We'll go back to maybe start frequency of 100 kilohertz is okay, maybe 50 megahertz. So now 10 megahertz again, we'll try. How does it look? This is how it looks. And amplitude 14 dBm amplitude. Harmonics are very low, and if you decrease the amplitude a little bit, harmonics goes down very fast, and at around 10 dBm you got a decent 40 dB down harmonics. Signal is very clean. So let's look at 20 megahertz. Same thing with 20 megahertz. We need to increase the span to view harmonic maybe. Stop frequency goes to 75 megahertz. And yeah, of course it decreases my resolution bandwidth, maybe 60 megahertz. Yeah, that's good enough. So you can see the peak, 10 dBm peak, and if you increase it, you see harmonics at 13 dBm output level. You see some harmonics, but they are very down, 43-45 dB down, or 43-45 dBm down, very down. So let's go to 50 megahertz now, and you see 50 megahertz, it got same output, around 10 dBm output. And let's go to 100 megahertz now. So I'm feeding in 100 megahertz, and now let's set the span to maybe 190 megahertz. So you got very clean 11 dBm, 10 dBm, exactly 11 dBm, 100 megahertz signal. Very clean, very nice. So at 100 megahertz, this signal is able, 100 megahertz is able to produce amplitude of 11.32 dBm. Very decent. This is the 120 megahertz, similar output, 10.4 dBm. So that's it for this video. We have successfully verified performance of this little distribution amplifier. So of course all the channels are isolated through transformers. It's very unique of a design. You will not find that many isolated transformer design. And distribution amplifier works really well. You can visit my website www.circuitvalley.com.